Assalamu alaikum everyone. This is Aisha from the Faculty of Engineering Sciences. Welcome to this online tutorial video. In this tutorial we will discuss some problems from chapter number 5 of Thomas Calculus that deals with the integrals, either definite or indefinite integrals, and then we use those integrals to find the area between curves. I am not going into the details of theoretical aspects of this chapter since we discussed them in detail in our class. I have picked some questions from previous assessments like quizzes or final exam of previous years. So let's start solving those questions. Our first question is to evaluate this indefinite integral. We studied some methods like direct integration or integration using substitution to solve such problems. Here this question is the candidate for substitution. So let's start with substitution. For this we let 1 plus square root of y equals to some new variable u, and we are changing the variable in the integrand. We need to change the variable of integration as well, that is we need to change dy in terms of some multiple of du. For this we differentiate u with respect to y, which gives us du equals to 1 over 2 into square root of y dy. Let's rearrange these terms and it gives us 2 into du equals to dy over square root of y. We have changed the variable of integrand and the integration as well. So let's put these values in the integral. In this integral, our integral is 1 over under root y into 1 over under root y whole cube dy. Before substituting these values, let's rearrange the integrand. Means let's take out 1 plus square root of y whole cube and combine 1 over square root y with dy. If you look at this term, this is exactly equal to 2 into du. So let's put all these values into the integration. This gives us 1 over u cube, since we supposed 1 plus square root y equals to u, and dy over square root y is equals to 2 into du. 2 is a constant, so it can be taken out of the integral. This becomes 2 into, if I take u cube in the numerator, this will become u raised to the power minus 3 into du. The integrand has been converted into simple term. We can use power rule of integration here. This gives us 2 u into minus 3 plus u raised to the power minus 3 plus 1 divided by minus 3 plus 1. Since the integral is indefinite, we need to introduce a constant of integration. Let's call it c. Simplifying this gives us u raised to the power minus 2, u raised to the power minus 2. This is 2 into u raised to power minus 2 divided by minus 2 plus c, and the final term is minus u raised to power minus 2 plus c. In the start we substituted 1 plus y in terms of u. We need to back substitute to get the answer in our original variable. Let's rewrite the last equation again, that is integral of 1 over square root y into 1 plus square root y whole cube dy equals to minus u raised to the power minus 2 plus constant of integration. In the start we suppose that 1 plus y square root of y equals to u. Let's put this value in this equation and we get minus into 1 plus square root of y whole raised to the power minus 2 plus constant of integration, and the last answer is minus 1 over 1 plus square root of y whole square plus c. Our next question is about finding the area between the region, and the question says find the area of the triangular region in the first quadrant, and region is bounded above by this curve, exponent of 2x, and the lower bound is exponent of x. The bound on the right hand side is given by x equals to ln of 3. First we try to sketch the region that is on xy plane, and the curve for exponent of 2x is given by a curve like this. This is exponent of 2x, and the curve that is bounding from the below is exponent of x. So the curve exponent of x is given by this one, and the bound on the right hand side is given by the line x equals to ln of 3. X equals to ln of 3 lies somewhere here, ln of 3, and this line x equals to ln of 3 intersects both the curves exponent of x and exponent of 2x at this point. Our region is that we are interested in to find the area is this shaded region. Here we have the region in the first quadrant only. And the first quadrant means the region is bounded from the left hand side by this curve, by this axis, that is y-axis, and on the y-axis value of x is 0. So we have only this region. The formula to find the area between the curves is given by integration from a to b f of x minus g of x into dx. F of x is the curve that bounds the region from above, and g of x is the curve that bounds the region from below. Means we are only interested in the region that is sandwiched between these two functions, f of x and g of x. In our case, f of x is given by, the upper bound is given by e raised to power 2x, and the lower bound, that is g of x, is given by exponent of x dx. Now come to the limits of integration. Here if you see, we have the region in the first quadrant, and in the first quadrant y starts from 0 up to, x starts from 0, and the upper bound for x is ln of 3, that is bound on the right hand side. So our limits of integration are from 0 to ln of 3. Let's integrate this function, and we have exponential function, and the integration of exponential function is exponential function divided by the derivative of the argument. In the argument we have 2x, so its derivative is 2. This whole term is divided by 2 minus integration of exponent of x is exponent of x as it is, and then we have to apply the limits of integration that are from 0 to ln of 3. Since this is definite integral, we do not need to introduce the constant of integration. Let's put the limit of integration. The upper limit is ln of 3, so this term becomes 2 into ln of 3 divided by 2 minus e raised to power ln of 3, minus the lower limit is 0, so this exponent of 0 is 1, so this is 1 over 2 minus exponent of 0 here becomes 1. If you see in this term, the argument of exponential function is 2 into ln of 3, and the property of natural log is this: if we have a term like this, we can write it as ln of x raised to the power this term, that is the multiple of natural log, and in this case we have a. So our term becomes e raised to power ln of 3 square divided by 2 minus e raised to power ln of 3, that is the second term, minus 1 by 2 minus 1 is minus 1 by 2, and 1 negative is outside the bracket, so this becomes plus 1 by 2. Here we have e raised to power ln of 3 square. Natural log and exponential function are inverse of each other, so these two terms cancel out each other, and we are left with 3 square divided by 2 minus. Similarly, in this term, exponential function and logarithmic function are cancelled out with each other, and we get 3 plus 1 by 2. This is 9 divided by 2 minus 3 plus 1 by 2, and the final answer for the area is given by adding and subtracting these terms. We get 2. So the area that we were interested in is 2 units. Question is about finding the area of the region that is cut from the first quadrant by this curve square root x plus square root y equals to square root a. First we write y in terms of some function of x, that is square root of x plus square root of y equals to square root of a. Let's take square root of x on the right hand side. This gives us square root of y equals to square root a minus square root of x. Squaring both sides of this equation gives us y equals to square root a minus square root x whole square. This is some function, let's say function of x, f of x, and the region is in the first quadrant only, so the curve that bounds from below is x-axis, and on the x-axis y is 0. And area is given by limits of integration from a to b. So we only have f of x, g of x is 0 here, so the integration of f of x dx. Here first we analyze the limits of integration. In the first quadrant, the region is bounded on the left hand side by y-axis, and on the y-axis x is 0. So our lower limits of integration is x equals to 0, and for the upper limit let's use this equation. This is, let's call it equation number 1, and for the upper limit we put y equals to 0 in this equation, that is equation number 1, and we get square root of x equals to square root of a. Squaring this equation gives us x equals to a as the upper limit. So this is our upper limit and this is the lower limit of integration. So let's find out the area that is cut from this region. So the area of the region is integration from 0 to a, and the integrand is square root of a minus square root of x whole square dx. Let's first open the square. In the integrand, this gives us a plus x minus 2 into a square root of a into square root of x dx. First term is constant and the second term is variable. So the integration of constant is a into the variable of integration, that is x. So this becomes ax plus second term we can apply power rule of integration here. This becomes x square divided by 2 minus 2 into square root of a, and here also we can apply the power rule. This becomes x raised to the power 3 by 2 whole divided by 3 by 2, and at the end limits of integration from 0 to a. Now let's put the limits of integration, that is for the upper limit first term becomes a square. When we put x equals to a in this term, this becomes a square divided by 2 minus this term in the denominator is multiplied with 2. This becomes 4 by 3 into square root a and a raised to power 3 by 2 minus the lower limit. X is involved in all the term. Here x is present in this term, there is an x, and here also we have x. So this whole term becomes 0. Simplifying this, we get, adding these two terms, we have 3a square divided by 2 minus 4 by 3, and here power of a is 1 by 2, and in this term power of a is 3 by 2. So 3 by 2 plus 1 by 2 becomes 4 by 2, which is actually equals to a square. So taking the LCM, first take a square common, and we have 9 minus 8 divided by 6 So the area is given by a square, 9 minus 8 is 1. So the area of the region that is cut from the first quadrant by this curve is given by a square by 6 units. The next question has been chosen from the final exam of fall 2020, and the question says find the area of the region in the first quadrant, and the bounds are given by line y equals to x, line x equals to 2, the curve y equals to 1 over x square, and the x-axis. First let's sketch the region, and the region is on the xy plane is the first part is line y equals to x. This is y equals to x in the first quadrant, and the next part the line x equals to 2. Line x equals to 2 lies somewhere here. This is the line, and the curve. Next bound is the curve y equals to 1 over x square. The graph for 1 over x square looks like this. This is y equals to 1 over x square, and the last bound is given by x-axis. Means we have the curve as the lower bound, this axis. This is x-axis. So our region where of which we have to find the area is this part, this shaded region. If you look at this region, we have two different curves that bounds the region from above. One from starting from x equals to 0 up to this point, and from this point onwards the upper bound of the curve is changing, and the upper bound in this case is y equals to 1 over x square. So our total area is divided into two regions, one from 0 to this part, and the next from this part onwards up to the line x equals to 2. Since the bound on the right hand side is given by x equals to 2, which is the highest limit of integration. This means a equals to the total area equals to a1 plus a2, where the a1 is area of this region and a2 is the area of the second region. In this part, we need to find out this point where both these curves y equals to x and y equals to 1 over x square intersect each other. From this point onwards the curve is changing. So let's find the point of intersection. For the point of intersection we have y equals to x and y equals to 1 over x square. At the point of intersection both these curves have same value. So let's put x equals to 1 over x square, and here x cannot be equal to 0 since x square is in the denominator, so we cannot take x equals to 0. When we cross multiply these terms, we get x cube equals to 1, which gives us x equals to 1 as the point of intersection for these two curves. Means for the area of the first region our limits of integration are from 0 to 1, and in the second region the limits of integration are given from 1 to 2, since 2 is the highest value of the limit. So let's find the area, and this is limits from 0 to 1. The integrand in the first case is this upper curve, this curve as the upper bound, and x-axis as the lower bound. The upper bound is the curve x and lower bound is x-axis where y is 0. So this is x minus 0 dx plus, in the second part from 1 to 2, the curve that bounds from above is this one, y equals to 1 over x square. So the integrand becomes 1 over x square minus 0 since the lower bound is x-axis. Let's simplify these terms. We get limits from 0 to 1 x dx plus integration from 1 to 2, and I am taking this term from the denominator into the numerator and the power gets negative, so this is x raised to power minus 2 dx. Here we have simple terms, simple algebraic functions, so we can apply power rule of integration. This gives us x square by 2 limits from 0 to 1 plus x raised to power minus 2 plus 1 divided by minus 2 plus 1 with the limits from 1 to 2. Let's simplify this term first. This is x square by 2 from 0 to 1, and in the denominator of the second term we have minus 2 plus 1. This gives us minus 1, so this is minus, and x raised to power minus 2 plus 1 is x raised to power minus 1. So let's take it in the denominator. This is 1 over x, limits from 1 to 2. So we get, let's put the limits of integration. For the upper limit, x equals to 1 in the first term. This gives us 1 over 2 minus lower limit is 0. So the whole terms become 0. Minus, in the second part, upper limit is 2. So this becomes 1 over 2 minus lower limit is 1. So this is 1. 1 over 2 minus 1 by 2 minus 1 gives us minus 1 by 2, and due to this negative sign we get plus 1 over 2. The total area is given by A equals to 1 by 2 plus 1 by 2. This gives us 1. So the area of this region, this shaded region, this part is given as 1 unit. This question requires us to find the derivative of this curve y equals to integration from tangent x to 0, and the integrand is 1 over 1 plus t square. Means we have to differentiate y with respect to x. So let's take the derivative, that is dy by dx on the left hand side, and on the right hand side we have d over dx of this whole term, that is tangent x to 0, and the integrand is dt over 1 plus t square. From here we have two choices to find the integration and the derivative of this function, of this curve. First we can direct integrate this term, apply the limits of integration, and then take the derivative with respect to x. In the second choice is we can apply the fundamental theorem of calculus. Let's solve this question with both methods. In the first part, dy by dx is d by dx into this term 1 over 1 plus t square is the integration of tangent inverse t, since our variable of integration is t, and the limits of integration are from tangent x to 0. Let's put the limits of integration in this term. This gives us d over dx, and the upper limit is 0, so this becomes tangent inverse of 0 minus lower limit is tangent of x, which gives us tangent inverse of tangent of x. This is dy over dx equals to d over dx. Tangent inverse of 0 is 0, since tangent theta gives 0 at theta equals to 0. So this is 0 minus, this is tangent inverse and this is tangent x. Both are inverse of each other. So this term cancels out with this term and we are left with x only. That is d by dx of minus x, and the derivative of minus x is minus 1. So we get dy over dx equals to minus 1. The derivative of this integral is minus 1. In the second method, we are applying the fundamental theorem of calculus. That is method number 2, and we are solving this using solving the integral and taking the derivative using fundamental theorem of calculus. Fundamental theorem of calculus says when you take the derivative of a curve or a function y with respect to some variable, let's say x, and the curve is actually the integration of some function, that is integration from constant a to some variable, and the integrand is some function of t dt. This says that you can directly evaluate the integrand at x, that is the upper limit of the integration. What does it mean? It means that when we have upper limit as some variable with power 1 and the same variable is the variable of the differentiation, we can directly evaluate this integrand as at the upper limit. And in this case, the function is f of t, upper limit is x. When f is evaluated at upper limit x, this gives us f of x. In our case, we have dy over dx equals to d over dx, integration from tangent x to 0, and the integrand is 1 over 1 plus t square dt. First, we change the order of integration to take the constant in the lower limit and the variable in the upper limit. This gives us d by dx, limit from 0 to tangent x. Integrand is same, that is 1 over 1 plus t square dt. Since we have changed the order of integration, a negative sign is introduced outside the integral. If you look at the theorem and compare the values, we have a equals to 0 and d by dx is same in both the cases. F of t is 1 over 1 plus t square, but here the difference lies only in the upper limit. In our case, we have upper limit as tangent of x. We first need to transform this limit, this upper limit, in some simple function or some linear function with power 1. So let u equals to tangent of x. With this substitution, our integral becomes dy by dx equals to d over minus d over dx, 0 to u. There will be no change in the integrand because there is no function of x in the integrand. This is 1 over 1 plus t square dt. Here again, if you see, we have the derivative with respect to x, but the upper limit is u. In the fundamental theorem of calculus, derivative is with respect to x and the upper limit is also x. So we apply the chain rule here. That means d by d, the same variable with derivative, that is u, 0 to u, 1 over 1 plus t square dt, and the product of du over dx. Our u is tangent of x, so take the derivative of this function. This is du over dx equals to tangent x, derivative of tangent x is secant square x. So put the value here. This gives us, apply fundamental theorem of this part, and according to that theorem we can directly evaluate this integral at the upper limit, and the upper limit is u, derivative is with respect to u, so we get 1 over 1 plus u square with a negative sign into du by dx is secant square x, this one. So here we have secant square x, and since we substituted u, we need to substitute back to get the answer in the original variable, that is in terms of x. So we have secant square x divided by 1 plus u is tangent of x, so this becomes 1 plus tangent square x. This part from the trigonometric identity is equal to secant square x, that is minus secant square x divided by secant square x. Using the trigonometric identity, these two terms cancel out each other and we are left with dy by dx equals to minus 1. That was the answer in our first method as well. This is the last question of this video, and in this question we need to find out the area of the region that is enclosed by the line and the curve x equals to y square. The line is x equals to y plus 2. So let's first sketch the region, and the region is in the xy plane. First curve is x equals to y square. The graph for x equals to y square is the parabola facing rightward, and the line x equals to y plus 2 is somewhere here, and this line intersects x-axis at x equals to 2. This is the curve for x equals to y square, and this is the line x equals to y plus 2. We are interested in this region. We have to find the area of this bounded region. So we have the formula for area as area equals to integration from c to d. The integrand in this case is some function of y, let's say f of y minus g of y into dy. Because we have x in terms of some function of y, and the bound on the right hand side is again in terms of some function of y. Also, we have to find out the limits of integration, and these limits are the values of y. That means value of y at this point and value of y at this point. These 2 points are the points of intersection of the 2 curves. So let's find out the limits. For the limits, we find the points of intersection of the 2 curves. For this, we put both the curves equal. This gives us x equals to y plus 2, and here we get y square equals to y minus 2. That is, shifting all the terms on the left hand side gives me y square minus y minus 2 equal to 0. This is the simple quadratic equation, and we can factorize this equation. That is y square minus 2y by breaking the mid term plus y minus 2 equal to 0. From these 2 terms we can take y common. This gives me y into y minus 2. From these 2 terms, from the last 2 terms, we can get plus 1 common, and here I get 1 into y minus 2 equals to 0. This gives me y minus 2 into y plus 1 equal to 0. From here I can write y plus 1 equal to 0 and y minus 1 equal to 0. This gives me y equals to minus 1 and y equals to 2. So this is our lower limit for the integration, and this is the upper limit of integration. So let's find out the area, and the area is a equals to integration. Now the value of c is, this is c and this is d. Value of c is minus 1, that is the lower limit, and value of d is 2, that is the upper limit. F of y is, let's say, y square, and g of y is y plus 2. The question here is how to identify which of the curve or which of the function is f of y, or the upper bound, the curve that bounds the region from above, and that the curve that bounds from the below. And in this case, when the integration is with respect to y, one curve is bounded from the right hand side and one curve bounds from the left hand side. In this case, if we have chosen the wrong functions, let's say we have interchanged f of y with g of y, we will get a negative sign at the end, and since the area cannot be negative, we will take the absolute value of the area. So let's integrate this function, and we get y cube by 3 minus y square divided by 2 minus 2y, and the limits of integration are from minus 1 to 2. Let's write the last equation again, and that is area equals to y cube divided by 3 minus y square divided by 2 minus 2y, and the limits from minus 1 to 2. Let's put the limits of integration. Here we have upper limit as 2 and lower limit as minus 1. Putting the upper limit in this term gives me 2 cube divided by 3, and 2 cube is 8. So I have 8 divided by 3. In the second term, y square is involved, so 2 square is 4. 4 divided by 2 minus 2 into y, that is 2 into 2 gives me 4. Minus the lower limit is minus 1. And cube of minus 1 is minus 1. So first term is minus 1 by 3. The second one, x square, and square of minus 1 is 1. So this gives me 1 by 2. Minus 2 into minus 1 gives me plus 2. Let's simplify these terms. In the first term, the LCM is 6. So in the numerator, I get 8 2s are 16 minus 4 3s are 12 minus 4 6 are 24. Similarly, in the second term, the LCM is again 6, and in the numerator, I have minus 2 minus 3 plus 6 2s are 12. This is the first value. 16 minus 12 minus 24 gives me 16 minus 12 is 4. 4 minus 24 is minus 20 divided by 6. In the second term, I have minus 2 minus 3 plus 12. 12 minus 5 gives me 7, and this is divided by 6. So adding these two terms gives area equals to minus 20 minus 7 is minus 27 divided by 6. Here we are getting area with a negative sign, but since the area cannot be negative, so we'll take the absolute value of this answer, that is absolute of minus 27 divided by 6, and this gives me 27 divided by 6. This is the area that is bounded between the curves, bounded between x equals to y square and x equals to y plus 2. Thank you so much.